So continuing the discussion in time-dependent perturbation theory, today we will discuss about the concepts of interaction picture, which will be very handy when we discuss matter field interaction in the later segment of this course, and Dyson series expansion, which is also one way of neatly writing the time-dependent perturbation theory, and it is more useful in dealing with systems like quantum fields. So let us start building up. So till now, we know that if suppose there is a Hamiltonian which drives a state which time evolves a state, and it is made up from two pieces. One is the free part whose solution we exactly know, and then there is a perturbation part or the potential part which has been added to it, in presence of which we do not exactly know how to solve the equations exactly, and we try to compute its time evolution or eigenfunction versions approximately under different perturbation theory expansions. So we know under Schrodinger evolution, if I ask this question, then the total Hamiltonian, if it is time dependent, also then this particular time evolution operator e to the power minus I integration of the Hamiltonian over dt will act upon the initial state psi 0 and give me the final state at time t. So this is the time evolution operator. You must be more familiar with time independent version of that, which is just e to the power minus I h dt upon h bar. So I'm missing an h bar in this, but in the more general case where Hamiltonian is expected to be time dependent as well, then the exponential has a integration of the Hamiltonian. Okay, so this is the standard Schrodinger evolution. Now what we are going to do is to define a new kind of interaction picture in which I define a new state psi interaction. So actually this I can write as a kit. So psi interaction kit that is given from the Schrodinger kit psi s at time t by just taking the exponential with respect to the free part of the Hamiltonian h naught. Remember, the h naught was just one piece in the total Hamiltonian. So that piece which I exactly know how to solve, exponential of that hits the wave function psi s, and whatever I get, I'm going to define it as a psi interaction psi I. Similarly, another piece of information which we are going to define is called the interaction version of operator. So what I do, I take the operator O and squeeze it between the unitary operators of the free Hamiltonian. This is the time evolution of a system when there were no perturbation. So e to the power I h naught t upon h bar from the left and e to the power minus I h naught t upon h bar from the right. So effectively it is u naught dagger and u naught u naught in the right hand side and u naught dagger on the left hand side. So where u naught is just e to the power free Hamiltonian upon h bar. So this is the way I'm going to define the operators evolution. Remember, in Schrodinger evolution, the full Hamiltonian evolves the state. I'm not evolving with respect to the full Hamiltonian, only the free part. Similarly, in the Heisenberg picture, the operator is evolved with respect to the full Hamiltonian. Again, I am not doing evolution with respect to the full Hamiltonian, only the free part. So therefore, I am in between. The state has been evolved and the operator has also been evolved, and we are in between. It is not being done with respect to the full Hamiltonian, but one piece of the Hamiltonian which is exactly solvable. How this is useful, it will be very clear in a couple of minutes. So let us go along with this. If any operator can sit here between u naught and u naught dagger from the right and left, I can put the free Hamiltonian also in itself. So suppose I take O as h naught itself. So then h naught will sit across these two unitary operators, e to the power I h naught t by h bar from the left and e to the power minus I h naught t upon h bar from the right. However, it so happens that this operator and this operator commute. Some Hamiltonian and its exponential commute among themselves. So therefore, I can flip this. So h naught can come on the left and this can go to the right because these two operators commute. If they were not commuting, I would not be able to flip. We are not numbers. So once I flip, this e to the power I h naught t h bar comes here and it unitarily acts upon the second part of the unitary operator. Effectively, I get a U dagger U on the right hand side of H naught, and ultimately I get H naught back. So it so happens that H naught's interaction evolved version is itself. H naught does not change under this interaction evolution. However, if I do the potential, as we discussed, potential does not commute, or the interaction Hamiltonian, the perturbation Hamiltonian, which I'm now calling as a V, it could have been H primed or H1, whatever notation you want. Since this does not commute with H naught, it will not commute with their exponentials as well, so I cannot flip anymore. So this flipping which I did in this step cannot be done here. So therefore, this will not be a unitary dagger, and I will not get a V back. So interaction picture potential is not equal to its original value. It changes, but the free Hamiltonian remains at the same value. Okay. With this information, we further go ahead and try to see what happens to the time evolution of the wave function in the interaction picture. So remember, we have defined psi I of t as just e to the power plus I h naught t upon h bar acting on psi s of t. This is how we had defined the state, interaction picture state. Remember, there is a plus sign here. Unlike the usual Schrodinger evolution where a minus IH naught, IHT appears. Okay, but if I go along, do the time derivative. So the time derivative will hit this part as well as this part. Both of them are time dependent. So from the first part, if I do, then the exponential will throw out a iota h naught operator and divide it by h bar and the exponential back. That exponential combined with the Schrodinger picture psi s, which is appearing here, gives back me the interaction picture wave state. So I get this extra factor I upon h bar times h naught times the interaction picture wave function back. And the second part, when the time operator hits the Schrodinger state psi s, I know the Schrodinger evolution happens with the full Hamiltonian. So that is what we have to do. But let us keep waiting and let us see where do we get up with this. So the first term is this, as we have seen. In the second term, I know that this will be equal to, so here let us elaborate upon this piece and let us see what do we get out of it. So e to the power I h naught t upon h bar acting upon d psi s upon dt, and I know that Schrodinger picture del I h upon dt of psi s is equal to the full Hamiltonian times psi of s at time t is equal to 0. Okay. So not time t is equal to 0 at the same time psi s. So therefore I can put for this expression can be written as e to the power I h naught t upon h bar, and for the time derivative of the Schrodinger picture I can write it as minus iota upon h bar, which is iota upon h bar going to the right hand side will become minus iota upon h bar. Then I will get a h times psi s, which can further be written as e to the power I h naught t upon h bar minus iota upon h bar. Then what I do, I have this h bar here, h operator here. I insert a minus I h naught t upon h bar and e to the power plus I h naught t upon h bar, and then there was a psi s. So I have just inserted an identity in between. What does it do? This part, if I look at it, is just again the psi I back. So what I am supposed to get for this, I am going to get e to the power I h naught t minus iota upon h bar will be common outside. Then e to the power I h naught t upon h bar. Then there will be an h, and then there will be e to the power minus I h naught t upon h bar, which is here, and then the psi interaction, which is this. So you see, ultimately I do get, after the time derivative of things, I do end up getting these two terms. I h bar upon h naught acting on psi interaction, and then the h, the full Hamiltonian squeezed between the free unitaries u and u daggers and psi interaction back. So together, if I combine them, I will get, so since this h naught can also be written as, this h naught can also be written as e to the power I h naught t upon h bar times h naught and e to the power minus I h naught t upon h bar. So I use this. So ultimately you can see both sides will have similar kind of structure. Only thing that here it will be h naught and here it will be h. So I will get e to the power I h naught t upon h bar from the left and e to the power minus iota h naught t upon h bar on the right, and in between I will have a h naught minus h. Okay, so that would be the, this would be the, so that will be the full description of the time derivative of the interaction. So probably I'm missing a sign in the next step, but anyway, this h naught minus h is minus of the potential. So there should be a minus over here, a minus of the potential, because remember the full h was h naught plus the potential, and then the potential gets squeezed between I h naught t and e to the power minus I h naught t to give rise to the V interaction. So I will get a V interaction over here, and left hand side therefore this should not have been there. So left hand side therefore will be d upon dt of psi I t, which now can be neatly written as I h bar d dt of psi I, that is equal to Vi and psi I. The boxed equation and this equation are the same thing. So now you see the interaction picture is like a Schrodinger equation evolution with the role of Hamiltonian played by the interaction potential, not just the potential but its interaction version. Interaction version meaning the potential is squeezed between u naught dagger h u, sorry, not dagger, u naught v and u naught dagger. Okay, the way we had defined, yes, no, the way we had defined u naught and u naught dagger was the other way. So let me write it once more. It is u naught dagger v u naught. So this Vi plays the role of the Hamiltonian for interaction kit. The interaction wave function evolves as if it is undergoing a Schrodinger evolution with only the perturbation or the potential terms interaction version playing the role of the Hamiltonian. Okay. All right. So the information which we just obtained by going to the interaction picture, that the interaction kit psi I, time evolves with Vi. Vi is the role, Vi is the potential or the perturbation Hamiltonian, and its interaction time evolved version, and that plays like a role and of Hamiltonian for the psi I, and you can evolve the system with respect to this new Hamiltonian and obtain at a future time what would be psi it. And since I know the relation between psi it and the Schrodinger psi s of t, psi I of t and Schrodinger psi s of t are related by this operation. If I know the left hand side, I will obtain the right hand side by just taking e to the power minus I h naught t upon h bar, or better way of saying that, multiplying e to the power minus I h naught t upon h bar to both the sides. So therefore I will also know this, what is the Schrodinger time evolved wave function. So interaction time evolved wave function will be obtained from the perturbation Hamiltonian, its interaction version, and multiplying the free parts unitary, I will get the Schrodinger picture wave function, its time evolved version. Okay, so this is a useful tool, as we will see, that if I just focus on the time evolution of the interaction picture, then as we saw that the time evolution is being governed by a unitary operator which is made from the perturbation potential or perturbation Hamiltonian completely. I'm going to write it like ui. Okay, so that is the ui between time t0 and t. So you start in the interaction picture some wave function or the kit at time t0, and some unitary operator takes you to some future kit psi I t. So therefore, if I take the derivative of this on the left hand side with the ih bar times del del t, so right hand side I will get ih bar upon del t, since there are two variables and I'm taking the derivative with respect to t, and while t naught is a fixed quantity, I can convert it into a partial derivative. Okay, and while psi I of t naught does not depend on t, so only derivative hits the unitary operator ui. So therefore, I get the structure that the time evolved version psi I of t is just this much. Its time derivative is this much, which I put on the left hand side, and right hand side is just the interaction Hamiltonian, as I know, vi, and psi I of t, which is this. So this is the derivative of psi I of t, and this is just psi I of t. All right. So I bring then this equation right hand side into the left in order to write neatly as ih bar time derivative of the unitary minus the interaction Hamiltonian vi times the unitary. They should together act on the interaction side and that annihilate it. So that means this operator acting on psi I should be 0. This is just coming from this expression and writing psi I as the unitary times psi I at initial time. Okay, and now this equation should be true for all wave function, not for just wave function. I'm not looking for a solution of this equation for what wave function it happens. I'm demanding that it should happen for all wave function, because given any wave function, I can go to its interaction version, and that interaction version will time evolve like this, and I will get this equation. So if this equation has to be true for all wave functions of the universe, that can only mean that this operator itself has to be 0. That means the time derivative of the unitary should be related to the potential, interaction potential times the unitary itself. So it should be unitary over here. Okay. So then I am just dropping the I notation in the u, because I will not write ui every time. I just write u, and it should be clear that we are talking about ui. So there, this equation is satisfied by the ui, the time evolution operator. Okay. In case of free Hamiltonian, I know the time evolution operator is just the exponential of the free Hamiltonian. In the interaction picture, in a presence of perturbation, in presence of interaction picture, I am trying to find out what is the unitary. Okay, so what properties of unitaries we are looking for? We want the unitary to satisfy a trivial identity that if I do not move in time, nothing should happen to the wave function. That means the unitary of no time evolution, t0 to t0, should be identity operator. So this should be 1 or identity operator. Further, as we have just seen from the previous expression, this should be respected. That means time derivative of unitary should be equal to this right hand side, which is this. That means if I do this integration over time on this side and integration of time on that side between t0 to t, left hand side I will get the unitary at time t minus unitary at time t0. Unitary at time t0 is identity. So therefore I can write as unitary as identity, or 1 minus iota h bar and this integration. So this is the structure of the unitary. It is an integral equation, that unitary at any stage is known from the integration of the convolution of the potential, interaction potential, and the unitary itself. Okay, that means it is an iterative equation, that I have this information. So you see, this is the t1, this is the t1, this is the t1, and this t1 is undergoing integration from t0 to t. So in between, whatever was the unitary, its total value determines what will be the unitary at a future time. Between t0 to t, dt1 takes the value, and unitary at all points during t0 to t, unitary along all points during T0 to T together combines with the respective interaction potential at all times and gives me a unitary at time t. So it is a convolution. It knows about its past. It knows about the history because the convolution goes from T0 to T with a variable T1. Okay. So therefore, again, I can use the same expression which we have just written here. The same expression, I can feed it back for u of T1. U of t is an integration of identity minus iota h bar over this integration. This I can feed up for u of T1. That means I can write down 1 minus iota h bar times Vi was there. Here it was sitting as u of T1 comma T0. So therefore I can write u of T1 comma T0 as again identity minus iota h bar. This time integration from running from T0 to T1. Previously the integration was running from T0 to T. Since I want to know what is u at T1 here, so therefore I have to run the integration from T0 to T1. So then a new dummy integration variable T2 will appear, and this will contain a unitary up to time T2, and T2 runs from T0 to T1. So you see, again I have obtained a u T2 which I can again feed in this equation's expression, and iteratively it becomes a bigger and bigger and bigger kind of integrations. So ultimately if I start collecting things, this 1 will be there, then this iota h bar times this quantity is multiplying the whole bracket. In the whole bracket there is an identity which first multiplies this outside integral, and I get the single integral dt1 of interaction potential Vi. Then this term here multiplies the outside term, then I would get a minus iota upon h bar whole square, 1 iota minus h bar from here and 1 iota minus h bar from here. So together they get the squared quantity. Then double integral, one integral here and one integral here. So dt1 of the interaction potential and dt2 of the interaction potential times the unitary up to second integration limit. And again you can feed the same expression back into u t2 t0, and this loop will start growing more and more. So you will get first zero integral, single integral, double integral. Again you write as a 1 minus integration of the third quantity. You will get a triple integral, then the fourth integral, a fifth integral, and ultimately it will keep building up. So you will get this kind of a structure: 1 minus iota upon h bar single integral, minus iota upon h bar whole square double integral, minus iota upon h bar cube triple integral, similarly fourth integral, fifth integral, and so on. And ultimately you can write it as a neat sum as identity or 1 plus a power series in minus iota upon h bar to power n and n integrals of Vi's. So this is the structure you will ultimately end up getting, and the last time you will do this would be you see the integration limit is shrinking. Initially it was the full range from T0 to T1. Then T1 was T0 to capital T0 to T. Then inside that the second integral came up with somewhere in between T1. This was just T. So in between there was some T1, and the integral ran from T0 to T1. In the third part, even the T2 came between T0 and T1. So the integral ran from T0 to T2. So similarly, the third integral will further go smaller. It will run from T0 to T3. And fourth integral will T0 to T4, where the size of the integral will keep shrinking down and down and down. And ultimately, it will reduce to a point T0 itself, where the unitary is supposed to be 1. So ultimately, you will get this series and the final U at T0, T0, which was 1. So therefore, I have a power series expansion. So I know the unitary from T0 to T as this simple power series expansion, minus iota upon h bar to the power n, the n integrals dt1 dtn, and then the vi's in between t1 tn So this is the structure of the unitary. Remember, in the ordinary free theory, unitary operator was just the exponential of the free Hamiltonian. That means in free theory, u naught was 1 plus minus iota upon h bar to the power n and h naught to the power n divided by factorial n. Okay, so we are trying to obtain the version of the unitary time evolution operator, which used to be the plain simple exponential in the free theory, to in the interaction picture some u, which is actually u of interaction, for which we have obtained expression, which is this integral power series expansion. Let us try to see if we can bring it into more neater form or not. And in order to do that, we are going to define something called a time ordering. That means which way we order time in the integrals. For example, let us take these two double integral, that is two integrals square, vi dt primed t0 to t, and its square would be just first I square. So I will do integration twice, one with respect to t1 running from t0 to t, and another time again with respect to another variable dt2 with that is also running for the same limit. That means that is meant by the square. Remember, in our expression we do not have this square. We have, for example, in double integral, the first limit runs from 0 to t, while the second limit runs from t0 to t1. Or you can interpret in other way that dt2 integral runs from t0 to t1, and while dt1 integral runs from t0 to t. So they are not running over the same limit. The second integral is running up to first variables up to t1, which becomes the first variable into the second integration, and that integration runs from t0 to t. We do not have a square at hand, but still I'm just writing a square over here and try to see where does that lead us to. So that square can be written as just a plain simple double integrals of the same limits. Then I define something called a time ordering on both these quantities. This symbol curly t is the time ordering. That means I will order the integral along the time direction. That is, I will do the dt2 integral up to the limit till which it is greater than the dt1 integral, and then vice versa. It will become in a minute what does it mean according to the time ordering. So the same integral which have the same limit t0 to t and t0 to t. That means I am thinking of two variables. One is the variable t1 and another is variable t2. Both start from t0 and this goes up to t, and the t2 also goes up to t. So I am thinking of a area of this square where both the sides are t0 to t, the first integral, and the t0 to t along the t2, which is the second integral. So I have to obtain the integration inside this square box. This square box can be broken into two triangles, a triangle in the upper half and a triangle in the lower half. In the upper half, following is true, that t2 is greater than t1. In the lower half, the other is true, that t1 is greater than t2. So therefore, this double integral of the same limit can be broken down into double integral over the two triangles. First triangle where t2 is greater than t1, and the second triangle where t1 is greater than the t2. So this is the upper triangle and this is the lower triangle. So here it was integral over the whole square. So now you see the picture like structure is coming about. We had similar kind of integration where t2 was running from t0 to t1 and t1 was running from t0 to t. So you see that in all this thing t2 was always smaller than t1. Its upper limit was t1. So this integral here is like the integral where t2 is smaller than t1, the lower limit, the lower triangle integral. So we had this integral at hand, while I know the double integral which I have written as a square over here is made up of two pieces. out of that one piece, the lower triangle looks like the integral which we want. So what do we do with the upper triangle? So the upper triangle can also be converted into a lower triangle integral, because you see the integrands are the same, t2, t1, and there is this t1, this t2. What I can do, I can relabel, call this thing as x and this thing as y. Then therefore this integral in the, so let us say first look at this lower triangle integral. Then the integral which we are running from, t2 is running from 0 to t1, and then t1 is running from t0 to t. I am doing a variable transformation in which I am going to call t1 as x and t2 as y. Then this integral in the lower triangle is equivalent to integration of dx with vi of x, and x runs from t0 to t, while the second integral is dy vi of y, where y runs from t0 to x. So this is the integral form. I'm just calling t1 as x and t2 as y. While for the upper triangle, I can again do a relabeling. I can get in the upper triangle, I am going to call t2 as x and t1 as y. If I do that, you can realize that even the upper integral becomes the same thing. There is a dy which runs from t0 to x, like here, and this x runs from t0 to t, like here. So you see, the upper triangle and the lower triangle are not different. They are exactly one and the same thing. So therefore, the full square is just double of one of the triangle, either upper one or the lower one. So I am going to write the full square as the time ordered full square, not on the time ordered full square as twice of the lower integral. And therefore the twice of just the lower integral will be 1/2 of the time ordered squared. So the integral which was appearing in my unitary, which was here, this integral, this double integral is just the lower triangle double integral we just obtained, which is 1/2 of the full square, both the limits being same and the full square. So therefore I can write the first term after identity as 1/2 of the whole square of the integration Hamiltonian, the interaction picture Hamiltonian. Remember, interaction picture Hamiltonian is just vi. Okay, so this is what vi get. Similarly, for 3 triple product integral which is appearing over here, triple product integral which is appearing in the next term over here, then that can be shown in by the same logic. It is 1/3 factorial times of 1/3 factorial times of the time ordered of cubic product. So the triple integral which was appearing over here would be 1/3 factorial times cubic product of the same thing. Similarly, 4 integrations will be 1/4 factorial quartic product of the same thing. And similarly, the nth integral, which appears in my expression, it will be just time ordered 1/n factorial times time ordered version of n product of the same integral. So therefore, the power series expansion which we just wrote down, which was here, I saw it is 1 plus minus iota upon h bar to the power n, and then n product. And now I know n product is nothing but 1/n factorial times the time ordered of n in the product of n integrals of the same limit, n integrals of the same limit. So therefore, the unitary which we are looking for, the interaction picture unitary which we are looking for, is 1 plus minus iota h bar to the power n, and the time ordered version of the n expansion, the n product of the integral. The time ordering operator can be taken out, then it just becomes 1 plus power series expansion of, so I had missed 1/n factorial was there, 1 minus iota to the power h to the power n, and then this integration of the interaction Hamiltonian to the power n divided by n factorial, which ultimately gives me exponential of the integration of the Hamiltonian in the interaction picture. Remember again, the potentials interaction version plays the role of the potential in interaction picture. So therefore, the unitary operator in the interaction picture is not just the exponential but time ordered version of the exponential of the effective Hamiltonian in the interaction picture. Remember, again I am to compare in the free theory it was just exponential minus iota upon h bar h naught t. This would have been the operator of time evolution. In interaction picture, role of h naught is being played by the vi, and role of exponential is going to be played by the time ordered exponential, and while the role of t is being played by this integration. So ultimately I have a unitary operator which resembles something like the unitary of the free theory, but not quite, because time ordering has come up and the integration in the exponential has come up. And therefore I can, using this unitary, I can take this unitary, act on initial state in the interaction picture and get the final state in the interaction picture. And once I have the final state in the interaction picture, I can get the final state in the Schrodinger picture by just plain simple multiplication of the free unitary u naught. So this is a game in which I can just focus on the potential or the perturbation Hamiltonian, do its time evolution with the free Hamiltonian, free unitary u naught, and then I get a vi which behaves as if it is the Hamiltonian of interaction ket psi I, and that psi I is related to the psi s through a unitary multiplication. Why we have done all this exercise? Because you can prove that if I am wanting to know expectation value of any operator, so either I can do in Schrodinger picture, I can take this operator, squeeze it between time evolved Schrodinger states, but you can prove that by multiplication. I know that psi s of t is nothing but e to the power minus I h naught t times psi I of t. Remember, psi I of t was defined as e to the power I h naught t upon h bar acting on psi s of t. So therefore, if I reverse this game, I will get psi s of t is e to the power minus iota h naught t upon h bar on psi I of t. And this psi s of t I feed here and I feed here. Then I get psi I of t, psi I of t, and then the free Hamiltonian's unitary on left and right, and this becomes the interaction picture operator. So as if I want to know expectation value, I can entirely work in the Schrodinger picture, or I can entirely work in the interaction picture. I just compute what is the interaction wave functions and what is the interaction operator. Their expectation value will correctly give me the expectation value of the operator in the Schrodinger picture. And it so happens in some of the discussions which we will have, doing computation in the interaction picture is more convenient than doing computation in the Schrodinger picture. None of them are different from each other, but mathematical convenience will be a guiding philosophy. So we will realize that for many of the computation which we will discuss later on, interaction picture becomes a smaller computation. So in using this philosophy and using this knowledge that the expectations value do not change from one picture to another picture. I can compute things in Schrodinger picture, or I can do computation of things in interaction picture. Answers will not change. Similarly, one can prove that even the inner product between the wave functions do not change under Schrodinger picture or interaction picture. So therefore, the probabilities, the projections, the probability, the coefficients, all these things in interaction picture or Schrodinger picture will remain the same. So therefore, I'm not going to lose any information by going to the interaction picture, where we will see in later classes that many of the computations become much more convenient and small. So better to work in interaction picture rather than a lengthy Schrodinger picture, because ultimately all information in both two pictures are the same. I can work in any of this, and I will choose to work in interaction picture in later discussions in this course, and there when you see, do not worry about why we are working in interaction picture, because all the information in interaction picture gets exactly mapped to the information we are looking in the Schrodinger picture. All right. So let us stop over here for this this analysis of interaction picture and the Dyson series. The Dyson series was this integral expansion of time ordered potential exponential. Okay, so we stop over here for the this class of time dependent perturbation theory.